Hello, am I audible? Hello, hello. Hello, am I audible?
Sir, we are live. You can start.
Yeah, so I mean, somebody just messaged me. So, okay, so shall I start now?
Recording in progress.
Shall I start now? Hello? Hello, shall I start now? Yeah, so I am Bhattacharya. I am from IIT Hyderabad. I'm an assistant professor here. So I work in the area of theoretical quantum information. So today I'm going to talk about the basic our idea is to convey the elementary message on quantum information science, and in that regard also we first need to understand what is quantum mechanics. So now, like every physical theory, we have a mathematical backdrop on which that is the theory of that is discussed. So for quantum mechanics, we need to understand basic linear algebra first, so that we can understand the backdrop on which quantum mechanics is discussed. So that's why this is that is the main reason for this lecture. So we will here discuss some basics of linear algebra, and we will only discuss this from the perspective of quantum mechanics. I want to remind everybody that in general the pure mathematical theory of linear algebra is much more vast, and or the theory of function analysis, so to say, is much more vast, and many of that is out of scope for our discussion. We will only choose that aspect of linear algebra that is indispensable for understanding the mathematical theory of quantum science. So that is the main goal. So if somebody is interested in basic linear algebra, from a mathematical point of view, then this can sure be an introduction, but that is a much vast and different area. So let us start that. So in classical, so let us, as quantum mechanics also was born somehow from classical mechanics itself, in some sense, of course, because everything was born from classical mechanics. So let us first try to understand how we describe the classical motion. So probably many of us, or most of us, or all of us know that classical mechanics is governed by the Newton's laws of motion, the three famous Newton's laws, which afterwards in the 300, 400 years, it has evolved and get complicated, and many different things has been accommodated in classical theory of classical mechanics. So after some time, for describing complex classical system, we do not use individual equation of motion corresponding to Newton's laws for all of the particles of a complex body. So we generalize the theory to something called first something called Euler-Lagrangian equation, and then something called Hamilton's canonical equation that comes from Hamilton's principle. But these things are just, we do not need to worry about that. What we need to worry about that for any describing any of such motion, we need a space, a coordinate space on which we describe the state of motion. In classical mechanics, that is dictated, that of course the motion is dictated by Newton's laws, or as I said, Hamilton's canonical equation, and the state of motion is described by a coordinate system which is called phase space. What is that phase space? Phase space, let's say we consider a point particle. So phase space is a space with all its position coordinates and its corresponding momentum coordinates. So let's say we are considering a three-dimensional motion of a point particle. So then therefore there will be three position coordinates x, y, z, and for each coordinates there is a corresponding momentum associated with that motion in that direction. So that is, let's say, px, py, and pz. So for that point particle, we have a coordinate space, which is the phase space corresponding to that particle, which is a six-dimensional space. X, Y, Z, three position coordinates, and px, py, pz, three momentum coordinates. Now, why position and momentum? Because to know the state of motion of a particle at any given time is completely described by its position, instantaneous position, and instantaneous momentum. So if we know the position and momentum of a particle in classical mechanics, of course, at any given time, then we know everything about the motion of that particle. So that's why we use this space called this phase space. Now for a point particle, it is a six-dimensional hyperplane space. For say n number of particles, if we consider a complex body having innumerous number of particles, let's say n number of particles. So the corresponding phase space will be, therefore, for each of those particles, it's a six-dimensional space. For n number of particles, it is a 6n-dimensional space. A point in that space is describes the state of the motion of the body, concerning body at that particular time. Now, any trajectory that is in that space is basically how its state of motion is changing. So by which we know the state of motion of a particle? By the equation of motion. So therefore, the trajectory in this phase space is governed by the equation of motion. That we say is Hamilton's canonical equations. I mean, for loosely speaking, we can also say if we know the Newton's second law of motion, then we know that. But in this particular representation, we don't describe the equation of motion by Newton's laws anymore. We use something synonymous to it, but in different description, that is this Hamilton's canonical equation. So we know that so the trajectory of the body in that phase space, and hence we know how its state of motion is changing in time. So that is how classical mechanics operates. Now, what about quantum mechanics? So, can we describe everything in quantum mechanics in phase space? Can we do that? Can we describe the position and momentum of a quantum particle in a given space, which is called phase space, and then we are done with it? Quantum mechanics is nothing new then. That is fine, but that is not the case. So, before going on, if anybody has any questions, please interrupt me. Any questions that need to be addressed, please interrupt me. So, quantum mechanics, what is the, what happens in quantum mechanics? So, we cannot describe the state of motion in quantum mechanics in the phase space. Why? Because of something, a peculiar principle called uncertainty principle. Heisenberg's uncertainty principle. In the 1920s, Heisenberg said that the position and momentum of a quantum mechanical particle or quantum mechanical entity cannot be known at a particular instant of time simultaneously. So, in other words, or in more technically speaking, position and momentum, or more generally we can say canonically conjugate variables, but position and momentum is fine for our understanding. Position and momentum of a particle, quantum particle, cannot be measured simultaneously. And so with complete precision. So, if for a quantum particle, we know its position perfectly without any error at a given instant of time, then we know nothing about its corresponding momentum. We cannot know. And vice versa. If we know perfectly a momentum of a quantum particle at a given instant of time, then we know nothing about its position. But in the meantime, we can come to a understanding sort of in this way. They say, okay, so to know both of them, let's say we know position of a particle with some error, then we can, there is a law or there is an equation that governs as an inequality rather, that governs the condition, then what will be the corresponding error in the corresponding momentum. And then with this error, we can sort of measure them simultaneously, but not perfectly. So we know that, therefore we understand that phase space is not sufficient or not adequate, I should say, to describe the state of motion of a quantum particle. So we cannot use phase space for quantum mechanical systems. So then what is the space? So therefore, and also quantum mechanics do not obey Newton's laws. So therefore what we need a new space, vector space to describe the state of motion of a quantum mechanical particle. And also we need to know a new principles of motion. So the principles of motion and how quantum mechanics behaves and what are the description of, say, this uncertainty principle and all other principles of quantum mechanics will be discussed later in a session dedicated to quantum theory. Here we are more interested, or we want to present a mathematical backdrop of quantum mechanics. So we are in our this lecture, we are concerned with the space part. That is, what coordinate space is adequate to describe the motion of a quantum mechanical particle. So that space is called Hilbert space. So in quantum mechanics, everything we know about a particle is encoded in a vector space, in a vector xi, let's say, here, in a space called Hilbert space. So what is that? So this vector, which is a element of this Hilbert space, is called the state vector. And the state vector, just like in, so let us try to do a little comparison with the classical mechanical case. So in classical mechanics, the space is phase space, where a point in that phase space describes the state of the motion. That is basically all of its components of position and corresponding momentum. Here, the space that describes the quantum mechanical system is called Hilbert space, and the state of motion of a quantum particle is described by an element of that Hilbert space, which is this state vector. And classical mechanics, as we said, is governed by Newton's laws of motion, or in other words, this Hamilton's canonical equation. Here, a state vector evolves in time according to Schrödinger equation. We will learn about Schrödinger equation later when we have a session on elementary quantum mechanics. I am introducing these notions of Schrödinger equation here because to validate why we are describing all this. That's it. The details of it will be discussed later. So, and observables are represented by certain operators. What are those operators? We will talk later, which acts on this Hilbert space. Operators are linear maps. Linear maps means map means so if there are any, I don't know whether it is possible in this format or not. If there are any questions that can be asked at any time. So what are these linear maps? Just a minute, it is, let me minimize this. Okay. So what are these linear maps? Linear maps takes an element of a Hilbert space to another element of the same Hilbert space. So the same Hilbert space is not necessary. It can take the element of a Hilbert space to an element of another, a different Hilbert space also. But let's talk simply, I mean, for the sake of simplicity, we are only considering this right now, that this linear maps takes an element of a Hilbert space, that is a state vector, to another element of that Hilbert space, that is another state vector. So that is a map. Now this map acts, this is linear. What is linear and all that, that will be described mathematically later. So why operators are important? Operators are important, there are, I mean, the class of operators is much more. The important of those operators are called observables. That is represented by a certain class of or certain specific type of operators. So why the observables are important? Because ultimately we want to know something about the quantum mechanical system. So a state vector, as I am saying, holds all the information wanting to ask. So will there be any questions? Anyway, so as I am saying, we need Hilbert space then. So the vector in a Hilbert space is called the state vector, as I was describing. So operators are linear maps. So and a special kind, there I was, there was a special kind of operation, operators which we call the observables. So they are essential in quantum mechanics. So what are the observables? And as I was talking, so state vector that holds all the information of a Hilbert space, of a quantum mechanical particle. So to know that particular information, it holds all the information, but to know the particular information, we need to do some operation over that of that particular state vector. Those are called observables also. For example, say its position of a particle or momentum of a particle or its energy. So the information is contained in that state vector. But how to know that information? So to know that information, we need to operate something, an operator, on that state vector to acquire or extract that information. Those operators are called observables. So there are also operators present or operators used in quantum mechanics, which are not observables. There are other kind of operators. We will understand in later what are those. So all these operators, be it observables or an operator which is not observable, has to be linear. What is a linear operation? We will talk about that later. So now we need to understand about this Hilbert space, and before understanding that, we need to know something about a space called metric space. So what is a metric space? Matrix can be a space, can be a vector space, or but we are only concerned about vector spaces. But it is more, the definition of metric space is more general. So a metric space is a space together, which is the space is given by this x, the capital X. So it's together with the distance function d, which takes two elements of that space to a real number. That is, a real number space is given by this R, capital R thing in bold. So that is a distance function that has to be present, that there should be a valid definable distance function present in that space. Then and only then it can be called a metric space. So the properties of that distance function is, it is positive, it is a non-negative. That is, so there is a difference between positive and non-negative, technically speaking. So we sort of understand that d greater than equals to 0 means it's positive. So it also, when it also includes 0, we call it non-negative. So this d, which is a distance between two elements of the space, the distance is a real number, it maps into a real number. So that always should be a non-negative quantity. It is only 0 if and only if x is equals to y. So the distance between x and y can only be 0 if and only if x is equal to y. So this distance should be a symmetric function. So that is, the distance between x and y is equal to the distance between y and x also. And it should hold these inequality, which is called all distance measure, valid distance measure is called, should hold this triangle inequality, which says that so distance between say x and z. So let's say you know triangle inequalities in your school, from your school days in fact. So let's consider a triangle. So 3 points form in general forms a triangle. So there is a distance x and y and z at 3 points, let's say. So that the distance between them. So they are the 3 sides of a triangle. So the sum of 2 sides of a triangle is always greater than the third one. So distance between x and z should be less than or equals to the distance between x and y plus the distance between y and z. So in general, this is more than the thing we understood in elementary geometry, but you can picture what this triangle inequality is. So all these 4 properties has to hold for a bona fide distance measure. So a bona fide distance measure is that which holds all these 4 properties. So if for a space, given space, there always exists a bona fide distance measure which can take 2 elements of the space to an element of to a real number, which holds this distance measure should hold all these 4 properties, then the space is called a metric space. So Hilbert space is a metric space. So a distance function, distance measure, in fact, many different distance measure can be defined, which holds these 4 properties. We will talk about some of those here in this lecture. So a Hilbert space is a vector space, and also it's a, it has this property of the metric spaces over complex number. So it's a vector space where elements can also be, magnitudes can also be complex. So vector space, we have a little idea about, for example, the Cartesian coordinate space that we understood, that we know from the school days, in fact. So that is a vector space defined on a, that's a real vector space, they defined on a real number. But in general, Hilbert space is a complex vector space, defined in complex numbers. So the Hilbert space is a vector space over complex number, complex vector space equal to the complete inner product. So this inner product is related to this metric space that we are considering. So there are other distance measures also. So this inner product can be understood as the distance function that is needed to be, that we need to have for a proper metric space. So we will talk about inner product later. But why Hilbert space is a vector space? Because vector space obeys certain properties. So what are these properties? So there has to, when you define a vector space, then some operation needs to be defined. For example, the addition operation. So Hilbert space obeys these 4 properties for this addition operation. So addition of 2 elements of a Hilbert space, that the 2 vector xi and phi, they obey this commutativity property, that is xi plus phi should be equals to phi plus xi. It also should obey this associativity property, that is you take 3 vectors in a given Hilbert space, xi, phi and chi. So you can first do the vector addition of phi and chi, and then add the resultant with xi. That is same as first do the vector addition of phi and xi and phi, and then adding the vector resultant vector with the final vector chi. So this property, as expressed in this equation, is called the associativity property. Identity. So identity operation is what? Identity is something, for example, before doing that, let's say, what should be the identity for addition operation? So to take any number, add 0 with it, the final number is the same number. So this property for an operation, so if for any operation there is an identity present, I mean not always definable, but for addition, subtraction, addition, multiplication, they can be defined. So for addition, even in number, the addition of number, the 0 is the identity element, because if you add it with any number, you will get the number back. So same thing for the vector also. So there should exist something called a null vector, which is represented by this small o. So if you add it with the vector xi, you get the vector xi back. This o is null vector, called null vector, and which is the identity for addition operation. So these are the properties of addition, additive properties of for the addition operation for a Hilbert space. So there is also some an operation called multiplication operation. So if you multiply a vector with a scalar, scalar means a number. Here, since we are talking about a complex vector space, so number should be a complex number. So this, for example, we multiply a complex number with two vectors gi plus phi. So this distributive property, property is the both are distributive, but distributive in different sense. First is distributive over H. H means Hilbert space. That is distributed over the vectors or the elements of the Hilbert space. So if a particular complex number is multiplied with the sum of two vectors, then this is distributed like this. It is equal to C of xi plus C of phi. So C of xi plus phi is equals to C of xi plus C of phi. And distributive over this C means C represents the space of all complex number. So the distributive over the complex number over that is scalar also. That is, you multiply the scalar a plus b with xi. That distributes also like a xi plus b xi. So these are the properties of multiplication of a scalar with a vector. There is also another multiplication possible here, that is a vector with a vector. What about that? So for that we need to know this thing that is called this inner product. So inner product is related to the distance function we talk about when we define the metric space. So what is that? So this inner product is a map, linear map, which is represented in like this two first parentheses and a comma between them. So it is what is the map? It takes two elements of a Hilbert space to a complex number. That is, it takes two vector and do some particular form of multiplication, so that the result is a complex number. And this map is a linear map. So this is given like this. So this has three properties: is conjugate symmetry, linearity, and additivity. So the inner product of two vectors xi and phi is a complex number. Is the that's why it is it's conjugate to its this phi and xi star. So phi xi star, that is complex conjugate of phi, inner product of phi and xi, is the inner product of xi and phi. Another property is linearity. Linearity in this sense that phi is, we are doing the inner product of phi with this vector a xi, where a is a complex number. Then this a comes out of this inner product, and this is equals to this complex number into the inner product phi and xi. There is a point to remember about this linearity. So in the first argument, if the complex number is associated or multiplied with the first argument, then it acts like this. A phi, inner product of a phi and xi is a star phi xi. So it is called antilinear. So it is linear in second argument, that phi Ai inner product is A into the inner product phi Ji, but it is antilinear in the first argument. That is, A phi Ji, inner product of A phi and Ji is a star phi Ji. And another is this additivity property. That is, if you do this inner product of phi with this addition of two vectors Ji and chi, so it is the inner product of phi Ji plus the inner product of phi chi. So if we take these linearity and additivity property together and do the inner product, say phi, inner product of phi and A Ji plus chi, then the output will be what? A phi Ji plus B phi chi. So sorry, I should rephrase. So the inner product of phi and the vector A Ji plus B chi. A, B are complex numbers. So that will be A inner product of phi Ji plus B inner product of phi chi. This can be very easily understood from this property 2 and property 3. So that is what a linear map is all about. So if map is a linear, then this property should hold. So that's why this inner product, which takes two vectors in a given inverse space and maps it into a complex number, is also a linear map. There can also be, we can define other distance function in Hilbert space also, many other distance function in Hilbert space, which are not linear, which doesn't have this property. But for metric space and all that, we need this property, this linearity, and some other aspects also, which we'll discuss later. So these are the properties, this conjugate symmetry, linearity, and additivity. And there are these 2 points to remember. First, we discussed that the inner product is antilinear in first argument. And the second one, so inner product of a vector itself is a real number, and it is called the norm of that vector. Norm is sort of its magnitude. So we can understand all these things from our idea of vector space that we already know from our school day geometry and algebra. So, for example, you know the Cartesian vector space, Cartesian coordinate, which is the usual vector space you know. So there you know the distance, all these properties hold, this triangle inequality, these. So there also you have this distance measure, which is, let's say, 2 point in a three-dimensional coordinate system be represented by x1, y1, z1 and x2, y2, z2. So we know that there is a distance that is given by root over x1 minus y1 square plus y1 minus, x1 minus x2 square plus y1 minus y2 square plus z1 minus z2 square. This distance function, you see, this obeys all the properties of proper distance function. So that is, it is always positive, non-negative. And when you take a distance with itself, of a vector with itself, it is 0, and only then it can be 0. It is symmetric also, and it also holds the triangle inequality property. So there also you can define, from this distance also you can define a norm. For example, you consider a origin, a norm of a vector can also be defined in that way. So you know that how it is done. So if a vector is given, say, xi cap plus yj cap plus zk cap, then its norm is root over x square plus y square plus z square. So that is how it is also, we can understand this whole thing from that point of view. So this inner product you can understand as the inner product of two vectors, you can understand as the dot product in that vector space you know. So the dot product of two vectors is what? A dot B. So that you know. But if you take the dot product of a vector with itself, you get its magnitude square, mod square. So that is the same thing here. So it is sort of, this inner product is sort of the generalization of the dot product you know from your idea of vector space from your school days. So it also gives you the property of this norm. Okay. So now what is norm? So when we have an inner product, we can define a norm of this form. So inner product of it is square root of inner product of a vector with itself. So norm is root over inner product of xi and xi. So there is a very important theorem, inequality rather, that is associated with the inner product and the norm of a vector. So that is called Cauchy-Schwarz inequality. So it says that, sorry, there should be a first bracket which is a typo in the here in the description. There should be a first bracket here. So the mod of inner product of two vector mod square of phi and xi. So why mod square? Because inner product of two vector is a complex number. So it takes the mod of that complex number, mod square of that complex number, is less than equals to the multiplication of phi and xi. So the square of the mod of square of the magnitude of norm of phi vector and xi vector. So this inequality is called triangle inequality. So this inequality is called Cauchy-Schwarz inequality, and triangle inequality is a consequence of this Cauchy-Schwarz inequality. So let us, Cauchy-Schwarz inequality. The proof of Cauchy-Schwarz inequality we'll discuss. Okay, let me discuss the proof of Cauchy-Schwarz inequality first. So let us discuss the proof. So suppose we take two elements of a Hilbert space, which are this x and y. X and y are the vectors of this Hilbert space. Suppose x is not a scalar multiple of y. So that is, x is linearly independent of y. If that is the case, and they are both non-zero, that is, none of x and y are zero vectors, and any of x and y cannot be represented by the other. So x cannot be represented by y and y cannot be represented by x. So they are linearly independent. We'll talk about linear independence again. So x minus alpha y, since x is cannot be linearly represented by y, so x cannot be written like x equals to alpha y or something. So x minus alpha y for any non-zero alpha, this cannot be represented by x cannot be represented by alpha y. So x minus alpha y is again another vector which is always non-zero because x cannot be represented by alpha y for any arbitrary non-zero complex number alpha. So this inequality trivially holds. That is, the mod magnitude of x minus alpha y square, she is always positive, it's strictly positive. So if we expand this mod thing, then we have what? Mod of x square. Just try to remember the multiplication of the sort of a plus b whole square formula in that sense also. So it's mod of x square minus alpha inner product of x and y minus alpha star inner product on y and x. Why the opposite happens? Star happens because y is in the first argument. That's why this is alpha star. Plus alpha star magnitude of y square. So let's say this alpha is a complex number. So we can represent alpha by this mu into t. Where t is sort of the magnitude of this complex number alpha. So t is real. And magnitude of mu is 1, and mu is basically, you can write as some mod mu to the power I theta, which is argument, complex argument. So therefore, where this inner product of xy is nothing but magnitude of x and y, inner product of xy into this complex part that is exponential minus I theta. So therefore, this mu xy, which magnitude is 1 basically, that is the magnitude of x and y. So therefore, the whole thing can be written as, since mu is magnitude of mu is identity, mod of x square minus twice t mod of xy plus t square mod of y square, that is greater than 0. So this LHS is minimum when this, since y is present here, this thing is equals to 0, which gives us the value of t is mod of magnitude of the inner product xy by mod y square. So if we put this here back, we get the inequality. But let me describe it in from a different, more detailed description. That would be better. Yeah. So let's say that I hope this handwritten note is visible. So this Cauchy-Schwarz inequality, let's say that this proof of this. Let's say u and v are the excuse me, non-zero vectors in Hilbert space H, such that they cannot be represented by a linear multiple of each other. That is, u is not a linear multiple of v, and v is not a linear multiple of u. Similarly, so this is called linear independence. We will talk about linear independence later. So this magnitude of this u minus lambda v, which is another vector, which therefore is not a null vector, since both of them, u cannot be represented by lambda v for any given lambda. So therefore u minus lambda v is not equals to 0. In fact, it is not a null vector, so its magnitude should be greater than equals to 0, the thing we were discussing. So now if we expand this, we have what? We have inner product of u, which is basically its magnitude square, minus lambda, inner product of uv, minus lambda bar, that is lambda star, complex conjugate of lambda, inner product of v and u, and lambda bar, that is lambda into lambda star, inner product of v with itself. That should be greater than equals to 0. So in norm notation, it is u and u is mod of u square, magnitude of u square, and v, inner product of v and v is magnitude of v square. So from the first and last term, we have mod of u square, magnitude of u square plus magnitude of v square into lambda star or lambda bar, minus lambda u, inner product of uv, minus lambda bar, inner product of vu. This is greater than equals to 0. Now if we choose lambda to be this quantity, since we can choose any lambda, because since u and v are linearly independent, that is, u cannot be represented by a scalar multiple of v for any scalar. So therefore we can choose any lambda, and this inequality will hold. So we choose this lambda, this lambda equals to inner product of v and u by magnitude of v square. If we put this here, we find what? Lambda bar is what? The bar of lambda, that is the complex conjugate lambda of lambda, is inner product uv by mod v square. So lambda bar gives you magnitude square of u and v. So this is mod of magnitude square of u, inner product of uv by, in the denominator we have v to the power 4 into we already have magnitude of v square. And this third and fourth term both, you see lambda is multiplied with the inner product uv. So the denominator is same for both, that is mod of v square. The numerator lambda into uv is what? Inner product of vu into inner product of uv. So that gives mod of inner product of uv square. Similarly, the same thing for the last term also. So this third and fourth term gives you twice of mod of uv, inner product uv square, by magnitude of V square. So you see the third term and fourth term we have mod of U square minus mod of UV square by V square. So we have magnitude of U square is greater than equals to, you take these on the right hand side, magnitude of UV square by V square, which gives us the Cauchy-Schwarz inequality. I hope this is clear. So let us now go back to our original presentation again. Is it visible? I hope it is. Okay. So, triangle inequality is a consequence of Cauchy-Schwarz inequality. How? Let me discuss. So, triangle inequality is what? Triangle inequality is magnitude or mod of U plus V, V plus W should be less than equals to magnitude of V plus magnitude of W. So that means that if we take the square of this, that is also valid. So square of the magnitude of V plus W should be less than equals to magnitude of V plus magnitude of W whole square. So if we take from there, so if the magnitude of V plus magnitude of W whole square minus square of the magnitude of V plus W, if this is a positive quantity, then triangle inequality holds. So let's take that, let's now expand. So first term is just usual A plus B whole square formula, because magnitude of V and magnitude of W are real numbers. So it is magnitude of V square plus magnitude of W square plus twice magnitude of V in magnitude of W minus magnitude of V plus W square. If we expand this, what we have? Magnitude of V square minus magnitude of W square minus inner product of VW minus inner product of WV. So you see VW is complex conjugate to WV, and this V square and W square are cancelling each other. So we have, twice of magnitude of V into magnitude of W minus twice of real part of the inner product VW. Since inner product VW is a complex number and W inner product of WV is a complex conjugate of V, then we know that if we take a complex number, say A, so A plus A star, that is its complex conjugate by 2, is its real part. So inner product of VW plus inner product of WV is essentially twice the real part of the inner product of WV. Now, I'm sorry, here in the last line here also, it is the magnitude of the inner product of VW. So now the real part of a complex number is always smaller than the magnitude of that complex number. So crudely speaking, let's say you have a complex number A, capital A, which is a small a plus IB, where I is the imaginary number root over minus 1. So now its magnitude is what? Mod A square plus P square, and its real part is only A. So it can be easily shown that the magnitude of a complex number is always greater than the real part of its of that particular complex number. So twice real part of VW is always lesser than the magnitude of the inner product VW. So this is real part of VW. Since it is lesser than that, so it should always be lesser than twice V mod W minus twice inner product of magnitude of inner product of VW. Why? We are subtracting even a greater quantity than real part of VW. Therefore, the total thing should be lesser than that. So the second one, since we are subtracting more, then this is lesser than this one. And this second quantity, this is nothing but, if it is magnitude of the inner product of BW, this is nothing but the, if we look closely, this is nothing but the Schwarz inequality. So therefore, Schwarz inequality tells us that this is greater than equals to 0. So therefore, this quantity is greater than equals to 0, and hence triangle inequality holds. So we can prove triangle inequality from Cauchy-Schwarz inequality. So triangle inequality is a consequence of Cauchy-Schwarz inequality. Therefore, the inner product, therefore the valid distance measure is we can define by the inner product, and therefore it's a metric space. Its norm can be defined, and it holds triangle inequality. It holds the property, the symmetry property. It holds the when you consider distance measure, and all the things are, so all the properties of metrics and all that are present here. So therefore, this Hilbert space is a metric space and a linear vector space. So these are the its essential properties of the Hilbert space. So everything can be, you can yourself check the whole thing, even if you don't have the idea of Hilbert space and all that, but all of you have the idea of the elementary vector space. For example, the coordinate space that we know is Cartesian coordinates, even polar coordinates and all that. So consider Cartesian coordinate system in 3 dimensions. So verify all the properties of the vector space. So the properties of the vector space that we described, this associativity, commutativity, distributivity of its additions and multiplication properties, all of them are equally valid for the coordinate space that we know of. For example, the Cartesian coordinate space. So all of these properties can be verified from the Cartesian coordinate system we know. So what will be the inner product? So the inner product in our Cartesian coordinate system can be understood as the dot product that we know between two vectors. So Cauchy-Schwarz inequality can also be verified for a Cartesian coordinate system, and triangular inequality I am sure you already know, but they also can be verified from the initial Cartesian coordinate system. So all the properties of this Hilbert space that I have described, though the notation can be different, but all of them can be understood from the idea of a vector space that you already have, that is this Cartesian coordinate system. So you can understand everything and verify yourself what I just talked about from the notion of Cartesian coordinate system you already know. So before going into a more strict or more quantum mechanics specific notations and discussions of this Hilbert space and all that, we need to understand one particular another thing, which is called this dual space. So why this dual space we are discussing, that will be clear even in fact in the next slide when we go into more specific discussion regarding quantum mechanics. So for any given Hilbert space H, we always have a dual space, this H star. What is this dual space, and what are the elements of this dual space? The elements of this dual space are linear maps, which takes an element of the Hilbert space H to a complex number. I am repeating it because it may sound a little complicated upon first hearing. So let's take a Hilbert space. As we have discussed inner product, we can understand. So inner product is a linear map, that we also can understand. Its linearity property we just studied. And it is a map. Why? Because it takes two, in this case, it takes two vectors of a Hilbert space to a complex number. So it is a linear map which takes a vector. Let's say we fix one vector. The first argument vector is fixed. The second one is the vector we take, and we do this inner product and we have a complex number. Therefore, it takes a vector out of the Hilbert space and it maps it to a complex number. So it's a map and it's linear, so it's a linear map. So there can be many other linear maps possible. One linear map we described, which is this inner product, and which is all we need for our purpose. But let's say imagine there are many other of such linear maps that can be defined, which takes an element of a Hilbert space, that is a vector, to a complex number. So all these linear maps, if we can form a space corresponding to all these linear maps on Hilbert space H, then this space is called the dual space of H. So that is an element phi of this dual space H star defines a map. That is a linear map. That is, if it is acted on A xi1 plus B xi2, where A, B are complex numbers and xi1 and xi2 are elements of the Hilbert space H, it's a linear map which is equals to A, this map over xi1 plus B, this map over xi2. And this map takes this xi1 and xi2 to some complex number. One way to construct such a map is to use the inner product. So inner product is in fact the most prominent example of such linear maps. So given some state phi, so let's say we fix the state phi, that is a vector phi, which is the first argument of this inner product. And we leave the space for the second argument. So we can take any vector out of the Hilbert space H and put it in this blank space in the second argument. Then the result is a complex number. So this map, as written here, if you can see my cursor, you will see. So here, this fixing the first argument, this linear map, so this inner product map, that is an element of this dual space, as it takes any vector from Hilbert space H to a complex number, and it's linear. So the linear property of inner product ensures that the map is linear. It is to be noted that any linear map of this Hilbert space H star, taking an element of the Hilbert space, a vector, to a complex number, can be constructed via inner product for some fixed choice phi. Now this is new information. So when we are saying that the dual space form is the space of all such linear maps which takes an element of the Hilbert space H to a complex number, then it's fine. One of those examples is this inner product. But this information tells us that any such linear map of this Hilbert space, of this dual space H star can be constructed via the inner product only. If we alter the choice phi, so for some fixed choice of phi, any of such linear maps of dual space H star can be constructed out of the inner product. We are basically talking about vector space, which are discrete vector space, finite discrete vector spaces. So this can also be extended to infinite dimensional system, that is by something called Rie's representation theorem. So okay, that is not essential for our primary discussion, but this is just for sake of general knowledge. You can understand that this Rie's representation theorem extends our concept, the concept we are discussing, to infinite dimensional system also. So now here, so up to this we discussed, oh, please allow me to have some water. Yeah. So now up to this we are discussing the notion of Hilbert space, the notion of inner product, the vectors and all that from a mathematician's point of view. Now we will be changing our notation a little, which is explicit for physics purpose. So we use this same concept of Hilbert space, inner product, linearity, observables, all that is predefined in the notion of Hilbert space, which is a subject of pure mathematics. We use this in for the purpose of quantum mechanics, where this element of this Hilbert space, that is vectors, are essentially represented the state of our quantum system. So all the information of a quantum system can be encoded in a vector of a given Hilbert space. But for explicit physics purpose, we change the notation a little. So the element of, so this notation was initially constructed by the famous British physicist P.A.M. Paul Dirac. After him, we call this notation Dirac notation, or we also call it bracket notation. So because the total thing, it looks like a bracket. So the element of a Hilbert space H, which is our, with space we concern ourselves. So the vector is represented by a vector like this. If you can see my cursor, you will see there is this sort of straight line, and then the notation psi, and this sort of boxed figure thing. So this is called a Kate vector. This notation is called Kate vector. Property does not change. The property of the vector is same as we discussed previously. Just the notation is changing, because in this notation everything will be a little more concise and easy to describe and understand. So the elements of a Hilbert space, the same vector that we discussed up till now, is now represented by this notation called Kate vector. And the dual space we just discussed. So that is basically, as we understood, that the inner product, where the first element of the inner product is fixed, the vector is fixed, and that gives us this linear map, which is the element of this dual space. So that is represented by this vector called bra vector. This is sort of mirror opposite of Kate vector. You see, Xi is same, and it is then the mirror opposite of K. The total thing defines this inner product. So if you take the inner product of phi Xi is this phi, bra vector phi, into then this Kate vector Xi. The total is called bracket. So these vectors, bra phi or here bra Xi, they are the elements of this dual space that we discussed. So basically, dual space is all the linear maps, and we can understand that all the linear maps which takes a vector to a complex number can be represented by inner product with a fixed choice of the first vector. So that notation is concised here in terms of this bra vector. So the bra vectors of the elements of this Hilbert space H star. So their inner product is basically the the complex number. So in this case, we sort of concise our notation. So given an orthonormal basis, okay, so I have missed something beforehand. Let me go back and I'm sorry, discuss that. Something called this orthonormality and linearity. So before going into the orthonormality, the linearity, let me discuss that. So as when I was discussing Cauchy-Schwarz inequality, I was discussing that we are taking two vectors x and y or u and v such that they are linearly independent to each other. That is, one cannot be a scalar multiple of other. So this is in general, what is this? Is called this linear independence. So let's say if you take a set of vector phi 1, phi 2, phi 1, phi 2 up to excuse me. So phi 1, phi 2 up to phi n. So they are linearly independent. So if they are linearly independent, if one and only solution to this equation, that is C1 phi 1 plus C2 phi 2 plus dot 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 up to Cn phi n is equals to 0. The only solution for this solution means what are the values of C1, C2 and all these coefficients. Is only the way it is possible if all the C1s are 0. All of them are 0. That is the trivial case. Otherwise, you cannot, this representing C1 plus phi 1 plus C2 phi u plus dot dot Cn phi n equals to 0 means what? Each and any of those vectors can be represented by all other vectors by a linear combination. If all the C's are, only solution is all the C's are 0, that means what? That means any of these vectors, if you take say 2 or 3 vectors, any of these vectors cannot be represented as a linear combination of the others. Just like we considered when we tried to prove Cauchy inequality. So the dimension of the vector space is the largest possible number of linearly independent vectors. So the next question is what? How many linearly independent vectors are possible in a given dimensional space? So let's say we consider 3-dimensional space. So then at most we can form 3 vectors we are linear independent of each other. 4 vectors cannot be linear independent of each other in a 3-dimensional space. So the dimension is the largest possible number of linearly independent vector that we can find in a given Hilbert space, in a given any vector space, so to say. So if there is no such number, the vector space, so that is no such number means it is limitless. You can take in, any number of vectors and you can form linearly independent vector for a given space. Then if there is no limit to this number, that means this vector space is infinite dimension. That is also possible. Now a more specific case, orthogonality. Orthogonality means, most easily speaking, perpendicular to each other is called orthogonal. But in our notation, if a vector, if we take an inner product of 2 vectors, let's say we take a set of these vectors phi 1 to phi n for an n-dimensional space, if inner product of phi n and phi j is 0 for all I not equals to j, and for if I equals to j, then it is constant, then this set of vectors will be called orthogonal vectors. That is, if we take the inner product with some other vector, it is always 0. Other vector of that set, of course, is always 0. But if you take the inner product itself, that you know is called the norm. So the norm cannot be 0. If the norm is 0, then the vector is null vector. So otherwise, if it is not multiplied with itself, it is always 0. If such a set of vectors are possible, then they are called orthogonal vectors. A very easy example, let's say we consider a 3-dimensional Cartesian coordinate system, x, y, z. So we take I cap, j cap, k cap as the unit vector along x-axis, y-axis, and z-axis. So you take the here inner product is dot product. So I cap dot j cap is what? 0. But I cap with itself, I cap is 1. 1 because it's unit vector. So these I cap, j cap, k cap are examples of such orthogonal vectors. If we normalize that, then we call it orthonormal vector. Like I cap, j cap, k cap in a Cartesian coordinate system. So how many? So orthogonal vectors, a set of orthogonal vectors are trivially linear independent. Not trivially, but they're the most prominent example of linearly independent vector. You cannot write I cap in terms of j cap or k cap, and vice versa also. So these are essentially linearly independent. The most prominent example of linearly independent vectors are orthonormal set of vectors. And therefore, how many, for a given dimensional Hilbert space, how many mutually orthogonal or orthonormal set of vectors can be found? That is also limited by the dimension of the given Hilbert space. So if we take a three-dimensional coordinate system as we are talking about, I cap, j cap, k cap. So x, y, z, I cap, j cap, k cap. Only 3 linearly orthonormal vectors maximum are possible. You cannot have 4 orthonormal vector in a 3-dimensional system. So that number of orthonormal set of vectors, maximum number of orthonormal vectors in a given dimensional space is limited by its dimension. So, and another point is any vector of that given Hilbert space can be represented by a linear combination by this set of orthonormal vectors up to the dimension. Just like any vector can be represented in a 3-dimensional coordinate system, Cartesian coordinate system can be represented by I cap, j cap, and k cap. This is exactly similar to that. So any vector xi can be represented as a linear combination of those orthonormal vectors. So what are these C alphas, which is this coefficients of those orthonormal vectors? That can be found by taking the inner product of this vector xi with this alpha orthonormal element, that is alpha orthonormal vector. If we take this inner product, we have this inner product of phi alpha and sum over alpha C alpha phi alpha. Sum over A in this case. So this is what inner product is linear. So CA will be outside, and then we have this inner product of phi alpha and phi A. Now we know these phi's are orthonormal to orthonormal. So when alpha is not equal to A, it is always 0. Alpha equals to A, then this inner product is equals to 1, and hence we have only C alpha. So each of those C alpha can be understood as the inner product of this vector xi with the corresponding orthonormal vector. Okay, so this idea is now we transform, all these idea in fact, we transform to our new notation, that is this bracket notation. The same thing that I described. So here also the vector space is everything is same, it's a Hilbert space. We just change that notation. So therefore in here also we can always define an orthonormal basis like this E alpha by this set of k vectors EA in this case. And any vector in a given dimensional Hilbert space can be represented by a linear combination of this orthonormal set of vectors, that is sum over A, xi A, EA. So here xi A, don't be confused, xi A is not a, I'm sorry, I should have represented by some C or something. It's not a vector, it's the complex coefficient of these EAs. So this any vector xi, it can be represented like this. So if we have a vector in this point, this chi, ket vector, which is represented by the orthonormal set of vectors CB with chi B. So then if we have the inner product chi and xi, what will happen? So we take the bra corresponding to this chi. So bra is just its sort of conjugate. What it is, we will describe a little in the end. And we take this inner product, we have this. The rule is like this. So chi, bra of chi is what? All these C ket vectors are becoming, CB ket vectors are becoming CB bra vectors. And these complex coefficients XB are changing to its complex conjugate, that is chi B star. So therefore we have what? Using its linearity property also, this inner product is chi B star xi A, inner product of EB EA, that is bra EB ket EA. And since they are orthonormal to each other, this will only be one when B is equals to A. So therefore we have this B index is now changed to A index. So we have sum over A chi A star xi A. So this is how a general inner product is defined in this notation, bracket notation. It is very useful to extend this idea to function spaces also. So it is an extension to this idea to continuous space. So we are usually we are considering the discrete system. So in continuum, this where this inner product thing for orthonormal vector, which is the ket, this bra A prime and A, where A is our orthonormal set of vectors. In discrete notation, we represented by something called Kronecker delta. That is delta A prime, which is 1 if A is equals to A prime, which is 0 if it is A not equals to A prime. In continuum, it is represented by something, this Dirac delta function, which is this delta, this is bracket A prime minus A. And the sum over xi A, which we represented in discrete notation, in continuum it is replaced by integration. And the inner product we just defined is also replaced by the integration and all that. Here we use some properties of Dirac delta function, but we have some other things to describe, so I am omitting this continuum part. So I am going to something called operators. So continuum also, I mean, one thing I can say that if you understand the discrete notation or the discrete Hilbert space, changing the language and extending ideas to a continuum is much easier. So operators now, and operators in a what are the operators now? So yeah, as we have discussing before, operators are also extremely important. So this initial sort of primary introduction, we should also discuss about operators. So the linear operator is a map which takes a vector of a Hilbert space to another vector. So here this A cap is this operator. Linear means A cap over C xi plus D phi is equals to C A cap over xi plus D A cap over phi. So that is the linearity property. All the operators we encounter in quantum mechanics are linear. Operators form an algebra. And what are the, given two operators, A cap and B cap, we define their sum as like this. I mean, these are the properties of the operators. This alpha A cap plus beta B cap is, when it acts on phi, it is alpha A cap. So the linearity holds here also in this opposite way also. Alpha A cap over phi plus beta B cap over phi for all phi in a given Hilbert space. So the sum of two linear sum or product of two linear operators is again another linear operator. The operator algebra is associative, that is similar as we discussed. an operator acting later before these B and C operators are acting. So if we operate the product of BC operator and then we operate the operator A, that is same as first operating the operator C, then operating the product AB. But operator algebra is not commutative. That AB operator is not always equals to BA operator. So this difference between two is known as something called commutators. It is given by this notation, this third bracket of A and B, which is defined as AB minus BA. So basically, if this vector sorry, we know that these vectors phi and whatever, these state vectors and all, they are vectors ultimately. So they can be represented by a column matrix. So basically, these operators are corresponding square matrix. So if we consider an n-dimensional vector, so this is the n cross 1 column matrix, then the corresponding operator should be an n cross n square matrix. We'll discuss a little about that also. So there are some properties of this commutator which obeys this, that is their antisymmetry. That is, the commutator of AB is minus of the commutator of B and A. It's linearity property, that is commutator of alpha A plus beta B, and C is basically alpha into commutator of AC and plus beta into commutator of BC. This third is called Libny's identity. This commutator of A, BC is equals to AB commutator of C plus B commutator of AC. And the fourth one is called Jacobi identity. So let us, I mean, I'm not going to discuss all the proofs. Let us discuss one or two for your better understanding. So first one is easy, basically antisymmetry, AB equals to minus BA. So take the commutator AB, that is AB minus BA. Take minus outside, we have BA minus AB. So that is the commutator of BA. Sorry, there is another sort of typo here, it will be BA. Linearity is what? Alpha A plus beta B into C. This, the proving this is easy again. So just expand it, alpha A plus beta B C, and we can rearrange by AC, EC and all that. Then we find that by rearranging this easily, in fact, we can find this is alpha AC plus beta BC. The third one is this Libny's identity, which is ABC. So if we expand this, we have A, BC minus BC, A. Now we add and subtract these two quantities, BAC. So ABC minus BAC now plus BAC minus this BC. Now you see, you can, from the first two terms, you can take C from the right hand side, take C common from the right hand side. So therefore you have AB minus BA into C, and for the last two terms you can take B from the left side. So you have plus B into AC minus CA. So you see AB minus CA is commutator of AB and AC minus CA is commutator of AC. So hence this Libny's identity is proven. So the fourth one, the Jacobi one, I leave it up to you to check. So there are also many other identities of these commutators and these operators can be found. So later maybe when I also have another discussion over basic quantum mechanics, I think on Thursday. So after that I will also give you some sort of assignment, you can say, and also some sort of homework you say. Only you don't have to submit the assignment. But you can check yourself and get really proficient on this algebra. This is not very tough. So a vector xi, so what is this now? We discuss some other properties also, this inner product thing. So basically A is corresponding to, say, A is the operator you are considering. So this plus thing is not plus, it's called Drager. So a dragger is what? A dragger is basically you take transposition of a matrix and also do the complex conjugation. So that is called a dragger. So we know that the usual eigenvalue, eigenvector form of a matrix, in fact. So since A operator, these operators, as we are discussing, a square matrix, they have, not always, but for if the matrices are normal matrices, then they always can be diagonalized. That they can have eigenvalues and eigenvectors. So these A J's are basically, if J is the eigenvector corresponding to the operator A, then A J's are the corresponding eigenvalues. So it is written as, in the right hand side, that is, and I hope you can see this, it is A over J is A J into J. So this is basically the eigenvalue equations. So these following identities are also true. I am not showing the proof of these identities. You yourself have to check them. So this inner product, so basically it is, later we will learn, it is also called expectation value if J phi, if phi and J are equal, same vectors. So this, if A, first we apply this A dragger, is again another operator over this vector J. So the output is again another vector. So we can take the inner product phi over that output vector. So that is basically inner product bra phi A dragger J. So that is basically the dragger of J, dragger or complex conjugate effect of J A phi. Where J dragger, a dragger of a kid vector is basically a J bra vector, corresponding bra vector. And the dragger of A plus B, this is also linear, that is A dragger plus B dragger. Dragger of A B is basically B dragger, A dragger. People who are familiar with matrix algebra, they know this. Alpha A, where alpha is a complex number, its dragger is A star A dragger. Dragger of dragger basically gives you the original operator back. Sorry. So these are the properties. So a dragger of the commutator AB is minus of commutator of A dragger, B dragger. This can be checked very easily. So this is the eigenvalue equation, A over J equal to A J over J. So this is only if J is one of the eigenvalues of this operator A, which can be represented by a matrix. And sorry, J are the eigenvectors. So then corresponding eigenvalues is A J, then A cap over J gives you the eigenvalue A J, and the repetition of the vector eigenvector J. If you take this conjugate, it will be bra, then vector J, then the operator A dragger is equals to bra vector J, and the conjugate of this number, that is the eigenvalue, is star. So there, I was also talking about the observables of which the operators which are, there are special kind of operators which are called the observables. What are those? Observables are the operators corresponding to something which can be observed. That is, the experimentally which we can check. For example, its position, its momentum, its energy. These are things that can be observed, that can be checked, that can be experimentally verified. So there are operators to theoretical representation of such actions of observation over a quantum mechanical state psi. So those operators are a special kind of linear operators that is called the Hermitian operator. What are those operators? Those operators are the operators whose dragger is equals to that itself. These operators are called Hermitian operators. They are extremely important in quantum mechanics. Why? Because, as I have said, they represent observables in quantum mechanics. They are very much they are sort of intrinsically connected with experimental observations and all that. So there is a property of Hermitian operator that is basically that the eigenvalue of the Hermitian operators are real. I'm not discussing the proof in general. Okay, so people who are, I expect most of you also are familiar with matrix mechanics, so you know Hermitian operator from your previous school day studies probably. So you know that the eigenvalues of the Hermitian operators are real. So that is the important thing, because eigenvalues are basically the observed quantities. I mean, it is more general than that, but loosely speaking now, the eigenvalues are sort of related to observation directly. So that's why in reality, something which you are observing should be represented by a real quantity. So here eigenvalues of a Hermitian operators are real. That's why they are the observables, because they can be observed in reality. So that is the most important class of operators in quantum mechanics. So we will discuss in this more technical parts in when we do the introduction of quantum mechanics in our next session. So, but something I want to discuss to have, I mean, for your better understanding. So why there are all these? Yeah, just a minute. Give me a moment. Yeah. I hope my screen is visible to you people. So again, showing you some handwritten notes, which if you want, I can share with you also. I mean, if the organizers tell me, I can share all these files, which can be shared later to you guys. So this is the bracket notation that I was discussing in my slides. This theorem is basically this Hermitian operator A is real theorem. So I mean, eigenvalues are real. I'm not discussing that. These I just told you that these alpha, any vectors can be represented by orthonormal set of vectors, complete orthonormal set of vectors. What do you mean by complete? So let us talk about that a little. So let's say alpha, as I have discussed before, the k vector can be represented like this, and sum over a prime, c a prime, a prime. The c a prime are the coefficients which are basically the inner product of these orthonormal vectors with the vector alpha. That is, c a primes are basically inner product. In this notation, therefore, it is dra a prime alpha. A primes are the orthonormal vectors. So if we now represent c a prime in this summation by a prime alpha and take the right hand a prime on the left side, then we have the representation of alpha is what? Sum over a prime, this a prime, then alpha. So this is somewhat similar to the vector notation. This first to a prime, so that is inner product is what? First we apply the bra vector and then the kth vector. We can switch it also. So first we apply the kth vector and then the bra vector. So this is a number, the inner product, and the opposite sort of multiplication is a matrix. This is called outer product. So if a set of orthonormal vectors is complete, then sum of all the outer products, possible outer products, gives you identity. That is identity matrix in this form. So why this is? So it is better to, all of these will be discussed later when we discuss quantum mechanics. It's better to just, I mean, for the teaser, discuss, the matrix representation if I describe to you, then I think it will be easier for you to understand or grasp the thing we just discussed. So the pardon me. So these k vectors we are talking about are basically like this. They are a column matrix. That is basically a representation of a vector. So k vectors are the column vectors, and the conjugate bra vectors are the row vectors with the elements to be complex conjugate of the elements of the k vector. So what is inner product? Inner product, we know first we apply the k vector and then the bra vector. So therefore, what we apply the bra vector and then the k vector. Therefore, first in the left is the row vector and then column vector. You know who are familiar with matrix mechanics that this gives you a number. The number will be A star A plus B star B plus all that. In general, it's a complex number. But what is this opposite one? If we first apply the k vector and then bra vector, what happens? We have the column vector first and then the row vector. And as you know, this gives you a representation of a matrix. So if these vectors are n-dimensional, so this matrix will be square matrix of n cross 1 elements. So any operator can be represented by these sort of outer products and all that. So all these will be discussed later. I don't think I should discuss right now because there are some other specifications will also be needed, and it will be a little cumbersome if I discuss all of this in one particular session. So this is the basic idea of linear vector space that we use in quantum theory so frequently. And as I have shown you a sort of teaser that how these vectors are basically gives you, in a different or a more detailed notation, they can be represented by column vectors and matrices. So therefore, basically what we will do in quantum mechanics, theoretical quantum mechanics here, regarding the linear algebra, is basically we will do matrix algebra. So that is the basic introduction. So what are the takeaway message? Takeaway message is that the state of a quantum system is completely specified by a vector k in a given Hilbert space. So these are some of, not all of them. So these are, one or two of them are the postulates of quantum mechanics itself. This first point that I'm talking about is basically the first postulate of quantum mechanics. The state of a quantum system is completely specified by a vector in a given Hilbert space. To every observable in classical mechanics, just like classical mechanics, we have observables like position, momentum, and all that. That can be calculated in classical way. So here in quantum mechanics, all those observables corresponds to a linear Hermitian operator. So that is also another postulate of quantum mechanics. As all the operator observables are represented by linear Hermitian operators acting over the Hilbert space. So contrary to classical mechanics, where in classical mechanics, the state of a classical system is described as a point in a phase space. What is a phase space? Let me remind you, it's a vector space with the position coordinates and the corresponding momentum coordinates. So a point in a phase space is basically gives you the position, all the position of momentum of a given classical system. And position and momentum, if we know the position and momentum of a classical system, we know everything about that classical system. But as we have talked here that quantum mechanics position and momentum are not simultaneously measurable, so phase space is inadequate to describe a quantum mechanical system. The quantum mechanics is described in a vector space is called Hilbert space. The basic fundamental properties of that Hilbert space we discussed in this session. And the measurements of an observable is given by this eigenvalue of a eigenvalue equation. So these are the basic take-home messages. I will share the document, and I also will share some other notes to the, if the organizers tell me, I can share it in them, and I can also share some, I will refer some books and notes also, but I will do that after my next session, that is the session on the elementary quantum mechanics. So after that, there is no point giving only linear algebra books, because we want to discuss linear algebra, as we have discussed, from the perspective of quantum mechanics only. So I will refer to some books and notes later after the next class, which will specifically talk about only the linear, idea of linear algebra from the, periphery of quantum mechanics. I will do that in the next class, but in the meantime, I can share some notes on this this presentation to the organizers, and they can share it with you guys. Okay. So if there is a question, so I am sort of ending my talk here, and if there are any questions, please ask. Anybody has any questions? Hello? Hello?
పై మొదటి ప్రశ్న, ఏ గ్రంథి వలన అధిక ఆవేశం కలుగును? ఆప్షన్ ఏ థైరాయిడ్, ఆప్షన్ బి అడ్రినలిన్, ఆప్షన్ సి పిట్యూటరీ, ఆప్షన్ డి అవటు. యువర్ టైమ్ స్టార్ట్స్ నౌ. ద కరెక్ట్ ఆన్సర్ ఈస్ ఆప్షన్ బి అడ్రినలిన్ గ్రంథి. ఎపినెఫ్రిన్ అని కూడా పిలువబడే అడ్రినలిన్ గ్రంథి విసరల్ ఫంక్షన్లను నియంత్రించే ఒక హార్మోన్ మరియు ఔషధం. మీ శరీరం ఒత్తిడి లేదా ముప్పునకు అడ్రినలిన్ గ్రంథి ప్రతిస్పందిస్తుంది. అడ్రినల్ గ్రంథుల ద్వారా మరియు మెడుల్లా అబ్లాంగేటాలో తక్కువ సంఖ్యలో న్యూరాన్లతో ఉత్పత్తి అవుతుంది. సెకండ్ క్వశ్చన్, భారతదేశ రైన్ నదిగా దేనికి పేరు? ఆప్షన్ ఏ గంగా, ఆప్షన్ బి గోదావరి, ఆప్షన్ సి నర్మదా, ఆప్షన్ డి కృష్ణ. యువర్ టైమ్ స్టార్ట్స్ నౌ. ద కరెక్ట్ ఆన్సర్ ఈస్ ఆప్షన్ బి గోదావరి. గోదావరి నది మహారాష్ట్ర నాసిక్లో ప్రారంభమై మహారాష్ట్ర, ఆంధ్రప్రదేశ్ రాష్ట్రాల మీదుగా ప్రవహించి రాజమండ్రిలో విస్తృతమైనదిగా గంభీరమైనదిగా పారుతుంది. దక్షిణ భారతదేశంలోనే అతిపెద్ద నదిగా గోదావరి నదిని పరిగణిస్తారు. గోదావరి నది చాలా ఉపనదులతో దేశమునందు 10వ వంతు ఆక్రమించుకున్నది. ఈ నది యొక్క మొత్తం పొడవు 1450 కిలోమీటర్లు. ఇది ఆంధ్రప్రదేశ్ లో 927 కిలోమీటర్లు